these numbers that we have in this array may be stock prices, and you want to study the trend of a stock prices for a given time interval, monthly, quarterly, weekly, bi-weekly. So you can think this range, this window, whatever you are given, that window is nothing but a time interval. So given a certain time interval, what has been the trend of the stock prices, and you are going to do some business logic and give the result of that. So don't get overwhelmed right now. Just think about it in step-by-step process. So we are given this problem. We understood the required data structure needed, the required concepts needed. Next thing what we have to understand is we have to understand the brute force way. What is the brute force way to solve this question? Hi everyone, welcome to my channel Code with Ease by Varsha. So this is the playlist on sliding window. So we have discussed about the algorithm and we have done some of the Leetcode questions so far. Why we are talking about this is because the question which we are going to attempt today is a Leetcode hard problem and it is based out of sliding window algorithm. So if you're new to the algorithm or want to brush up on the basics, I would recommend to go through this playlist, understand the concepts, revisit them, attempt a few questions and then come to this video. So let's move and see what is this question that we are doing today. So we are going to solve today's sliding window maximum. So what do we need to do here? We are given an array of integers. We're given an array of integers and there's a sliding window of size k, which is moving from left to right. We can see only k numbers in the window and each time the window is moving right by only one position and we have to return the max sliding window. So what does it mean? That the window size in this example is 3. So if I take the window size of 3 integers, 1, 3, minus 1, my maximum element is 3. So I have 3 in the output. Again, if I slide by 1, so my new window is 3, minus 1 and minus 3. My new integer is 3. Again, max in this particular window is 3 itself. Again, if I shift it, now my window is minus 1, minus 3 and 5. What is my max number? 5 and so on. So this is what we have to do. So the array which we are going to compute and return, at every index it is going to store for that given window of size k what is the max number. So now how do we solve this question? But before we try to solve this question, it's very important for us to know what is the real world implication. Why do we need to solve this kind of question? What is the real world impact? Okay, so you can think of it, these numbers that we have in this array may be stock prices, and you want to study the trend of a stock prices for a given time interval, monthly, quarterly, weekly, bi-weekly. So you can think this range, this window, whatever you are given, that window is nothing but a time interval. So given a certain time interval, what has been the trend of the stock prices, and you are going to do some business logic and give the result of that. So it can be something like that. It can be something based on temperatures, like weather forecasting also, to understand the trend of the temperatures. So anything for analysis, reporting, on the business side, if we try to think of, there can be many such scenarios. So this question is important from that perspective. Another thing that we also have to understand before we try to attempt is there's a concept in Q which is called monotonic Q. So it comes from the word like monotonous, something which is just like in the same similar pattern, boring pattern, same throughout, something like that. So monotonic Q is something which we have to understand before we attempt, before we try to understand more on this. So monotonic Q is of two types. It can be increasing or it can be decreasing. So what happens? Again, you need a good understanding of Q data structure also first before attempting this question. So what happens in case of increasing monotonic Q? As many of us already know, Q works on the FIFO principles. How it works? You add an element here, and then when you add the next element, it is added at the back of the queue, and then the next. So in case of increasing monotonic queue, what happens is, whenever you add an element at the back of the queue, the elements at the front are always going to be smaller. So it's as simple as you're adding in the ascending order. The elements that you add at the back of the queue are always greater than the elements that is already on the front. So that is why it is called increasing monotonic queue. And the same goes for decreasing, just the opposite. It can be like 4, 3, 2, 1. You're adding in the descending order. That's it. So this concept is necessary because we are going to make use of this concept over here. One more thing which we also have to understand, the data structure that we are going to use is called DQ or DEC, which we popularly know, which is also known as doubly ended queue. So normally queues that we use are mostly one single ended. So we add only from, like we add just at the rear or the back of the queue and remove it from another end, right? But over here, in case of DEC or doubly ended queue, we can add and remove from both ends. Usually we add at one end and remove from another end, but here we can add and remove from both ends. So don't get confused or don't get worried about these APIs and methods. When we will see the code, we will also go to the IDE and see this DEC class and what are the methods. So don't get overwhelmed right now. Just think about it in step-by-step process. So we are given this problem. We understood the required data structure needed, the required concepts needed. Next thing what we have to understand is we have to understand the brute force way. What is the brute force way to solve this question? That can be the one thing which can come to our mind. See, you're given this list of integers, right? Array of integers. What I have 1, 3, -1, -3, 5, 3, 6, 7. Now, if my window size is 3, how many windows can I form? How many windows? N, if it is the length, minus k. So my length is how much? 8. 8 minus 3, which is 5. Can I form 5 windows? Let's see. 1, 2, then again 3, then I have 4, I have 5, and I have 6. That's it. 6. So I have to do plus 1. So it is going to be 5 plus 1, 6. So this is the formula to calculate how many number of windows I can have given this. Now, how will I do this in the brute force way? The very first thing which will come is we consider one by one every window. So if I have to consider one by one every window, first I'll take a for loop and I'm going to run it. If I'm taking like int I equal to 0, I'm going to run till n minus kth index. I have to stop over there, which is in this case 8 minus 3, which is 5, set index number 5, 0, 1, 2, 3, 4, 5. Over here I'm stopping because 5 plus 3, this is my last window. So if I am at, so now I took first index, the first element, I have to run another loop where I will actually have my window size. What is my window size? K. So that is going to run always from 1 to k. Now inside this inner for loop, I have to actually do the computation to find out what is the maximum. So every time at the start, I'm going to initialize my max to nums of I, my current number. And I'm going to simply check if by doing the math.max, if my current number math.max, it's a usual check. Current max is greater or the number you are at. What is the number you are at? You are at jth number plus I because it is relative. 1 to k is 1, 2, 3 all the time 1 to 3. But that you have to add to your outer index value. So this is your max. And finally, you have to you're storing the max over here. And finally, so you're computing the max over here. And at the end of this, at your new array, you have to populate your max. Because the array which you have to return should have the max value defined at every index. We have discussed about it. So this is the brute force thing which we are doing. 2 loops, 1 loop running till the last index. I mean not last, wherever the possible index is. Inner for loop is running for the window size 1 to k and we are getting the max. Simple. This is what we want to achieve. What is the problem with this? The time complexity. What is the time complexity coming to be? Inner for loop is running k times. Your outer for loop is forming n minus k plus 1 windows and that is running k times. So we can generalize this and we can say it is running n into k times. So this is the time complexity that you have into k every time. So our next goal is of course to optimize. We need to optimize it and this is where we will come to our concepts of monotonic increasing queue and the deck. So what do we do now? What do we do now? What is our required time complexity? What is our required time complexity? Of course, we want to do it in O of n, preferably in single traversal. Now, let's talk about deck. Why we are going to use deck? The deck we are going to use because it gives us constant time when we want to add or remove elements from both the ends. From both the ends. Now, why do we need to add and remove elements from both the ends? This might be the question. Talk about the monotonic increasing queue again here. What I'll do, I have a queue here. Suppose my window size is k here. What I want, every time I add my element to the queue, I want to ensure that if I have 3 elements over here, 1, 2, 3, I want to ensure the element at the front is always going to be the max element or maybe the index of the max element. So every time given a window size of k that is equal to 3, I want to ensure my deck always consists of the max element at the front. If I'm keeping the max element at the front, obviously I'm making use of the monotonic concept, monotonic decreasing. So I have the max and the next elements are in decreasing order smaller than the max element. Again, I'm saying element, we are going to store the index, not the element itself, because it's easier to calculate. Okay, so we have monotonic decreasing. Now the question arises, okay, I have the max element at the first, which I can conveniently access by doing a peek. I can use peek first. So again, those who are not aware of peek, pop, pop is a stack concept, peek, pole, offer. These are queue concepts. Peek means to see, just access. Poll is to remove. Offer is to add. So I can just do a peek first and get the max element. So we are getting the monotonically decreasing order over here. Now, why are we doing this? A very simple example will be, take this particular example, 1, 3 and -1. So if I take this particular example and I have a queue, what am I saying? I will add 1 because the queue is anyway empty. So I'll add 1. Fine. Next, when 3 is coming, my window size is k. Okay. So window size is not met yet. So when 3 is coming, I see that my current element, which is 3, is actually greater than what I have in the queue. But I should always have the max element. So I'll remove 1 and I will place 3. So at the front, 3 is being pointed to. Like the front pointer is pointing to 3. 1 is removed. I want to maintain that max element is always there at the front. Now I go to -1. My current element is -1. Now I see that -1 is smaller than 3, which is fine. So at first I can have the bigger element. After that I can have a smaller element. So I'll add -1. Now my window size is reached. Now when my window size is met, at this first position of the output array, I can conveniently do peek first and get my max element, which is 3. Again, we are storing index. I'm just saying, just for the sake of convenience, we are going to do peek first and get the max element. So we're just obtaining the max element from the front of the DQ or the deck, so that anything, so we are just obtaining the max element from the front of the deck, and we are ensuring this monotonically decreasing order, so that every time we just go and grab the max element by doing a peek first. So this is where the concept of monotonic decreasing queue comes in. And this is where the concept of deck comes in. Now, again, think of it. You are taking one element every time you're traversing through it. You're just doing a single traversal. The adding of an element which you're doing is giving you constant time. The removal of an element, like we did, we removed one, is also doing constant time. The peek first, the accessing of an element, is also giving you constant time. So all the operations that you're doing is constant time. You can remove and add from both the ends. So everything you're being able to do in constant time, and you're just traversing the array. Single traversal. 0 to n. That's it. So this is the reason why the concept of deck comes in. This is why the reason of monotonic decreasing queue comes in. Why it is decreasing? Because again, if the max element is at the first, we can conveniently access it by using the peek first. Rest of the elements are in smaller order. So whenever now, if you want to remove elements which are out of the window scope, or the remove elements which are smaller, I can conveniently do it. So like I said, before 3 there was a smaller element, I removed it. It is convenient. Before 3 I have, let's say, something which is not falling in my window scope itself. We will see that in dry run. Remove it. Roughly, what is my algorithm going to look like? Number 1, my queue will always contain elements which are in my current window scope. Contain window scope elements. Remove anything which is falling out of window. This is my first requirement. Why? See, this window, I'm only containing this. The moment I add something over here, I have to remove the element which is falling out of my window scope. What is the second requirement? The monotonic decreasing order I have to maintain. Whenever I'm adding anything to my queue, I have to make sure first the max element and then the rest of the elements. If this pattern is maintained, then only I add the current element. Remember this, like 1 is removed, then I add 3. When I add 3, after that when I add -1, I ensure that monotonic decreasing pattern is there, then only I add my current element. What is the fourth step? Once I do that, to get my max, if I have to grab my max, I'm going to do a peek first from the queue, the first element of the queue. When I'm going to do this fourth step, when my window size is achieved. When my window size is achieved, I'm going to do a peek first and grab my max element from the queue. So roughly these are the steps which we have to do for the algorithm. So now before we do a dry run with the code, let's go to the IDE and see the operations that we can do with the deck queue and the operations which we can do with the deck, so that when I show the code, it doesn't look alien to you. So let's go to the IDE. Okay, so this is the main method. This is the main, and here is the class, the array deck. So this deck is an interface, and in Java you have certain implementations. Array deck is what we are also going to use. So as we can see, we have the constructor, blah blah, and then we have the main important APIs. We have add last, insert the specified element at the end of the DQ. Then we have offer first, if you want to insert a specific element at the front of the DQ. Okay. Then you have poll first, you have remove last, remove first. So I've written this program. So if we run this, we will get to know it even more clear. So we have done offer first, offer last, adding at the front, adding at that. So now if we run this, see the output. First, after adding the element, it looks like 3, 1, 2, 4. We have added the element 1 and then we have added the element 2. Okay. Then we offer first. At the front we have added 3 and then at the end we have added 4. So 3 and 4 is like at the boundary, at the extremes. Then when I'm doing poll first, what is at the front? 3 is there. So I'll doing poll first. Like the one we are doing when we are removing elements from the window, out of the window. We will do poll first. Then I'm doing poll last. If I want to remove from the end, what is there at the end? 4 is there at the end. So I'm going to remove from the end. Similarly, accessing peek first, what I was saying, to grab the max element from the front of the queue. We're going to use peek first. So just to familiarize you guys with the APIs, the methods that we have in deck, I just covered this portion. Now let's see the code for the sliding window maximum. So here's the code for this. So as we can see, we have the array deck first, the initialization done here. So as we can see, the array deck first is initialized. Then we have the output array, which we are going to return. N minus k plus 1, the logic I've already told, the number of windows that you're having. Then we have a for loop, only one for loop. First step, what we are doing? We are running a while loop. This is important. We told that the first step is to remove elements which are out of the window. So of course, if you want to remove or add or whatever, you have to check if the DQ is not empty. Then what do you check? If the dq.peak first is less than I minus k plus 1. So now this computation is important. I minus k plus 1. So peak first is going to be what? The element which is there at the front of the DQ. So anything if I have to remove which is out of my window scope. Okay, imagine this. So I have 1, 3, 5, 6. What are my indices? 0, 1, 2, 3. So peak first, 1. Okay, so now suppose I am at 6. What is my ith position? 3. What is my k? 3. 3 minus 3, 0. 0 plus 1 is 1. So anything which is lesser than 1. Here when I say 1, 1 is the index. So anything which is lesser than 1 index is falling out of my boundary. So if my window size is 3, anything which is lesser than 1 means of course the index 0, the element at index 0 is out of my window. So this is what we are doing. If the element at the front of the queue, any of them is falling out of the window, I have to do this. If they are, I'm removing it. Poll first, like I said. Peek first, poll first. If the element at the front is not falling in the window scope, remove it. I will keep on removing it until they are not, until I get the elements in my window. That is why the while loop. If after we do the DQ is, so after you have done this check whether the DQ is empty or not, now see this condition. This is important. Now see this condition. This is important. What are we doing? We are now taking into consideration the peak last, means the element which is being pointed by the rear pointer. There are 2 pointers, front and rear. Right? So we have already taken care of the elements which were in the front of the queue by doing a peak first and poll first. So those are already taken care of and they're out of the window, so they have been removed. Now coming to the remaining elements. If there is a case, if the remaining elements are also lesser than my current element, then I have to remove it, because as I told, I have to ensure this monotonically decreasing order. If something I still have in my queue which is smaller, then I cannot have it at the front. I have to remove it. So if I have 1 already and I want to add 3. So if I want to add 3, 1 is smaller than 3, I have to remove it. So that is why again this is running inside a while loop where we are checking by doing a peak last. If any more elements is left which is falling inside the window, it is falling inside the window but it is smaller, remove it, because my max, the one I want at the front, is only going to be the max element. So I will remove it. So this is about the step 2 and 3. First we remove the elements out of the window. Second, we remove the items which are smaller than the current. Fourth point, like I said, then you can safely add your current element. So offer last is like you're adding at the back of the queue. Finally, what is the fifth step? Now we actually have to start adding into our output array whatever is the maximum element. So this is the check that we are doing. If I greater than equal to k minus 1. Now why are we doing this check? This is also important to understand. So suppose these are the indices that you have and your range is 3 elements. Window size is 3. So when you reach over here, I is equal to 2 and k is equal to 3. Is 2 greater than equal to 3 minus 1? Yes, it is true. So your window is successfully done. Now when you are at 3, or maybe you are at 4 index, or you are at 5, at every index position, we have to populate our output array. So that is why we are just initially doing this check, so that for index number 0 and 1, by mistake, we do not miscalculate the window. The check is necessary so that for every index, now suppose if your I is 3 and k, we know that it is 3, right? So 3 minus 1 is 2. We know that 3 is greater than equal to 2. So anytime your k, if your k is 3, 3 minus 1 is 2, your I will always be greater than equal to k minus 1. From where? From this particular index going forward. So for every index, you're going to have a window, you're going to have a valid window, and you're going to populate it into your output array. That is why we are doing this check. And finally, like we said, how are we getting our max element? We are doing a peek first. Peek first is the operation we are doing to get our max element. And ultimately, we are going to return our array. This is the output array. So in this way, by 1, 2, 3, just 4 steps, like we have written over here, in just 4 steps, we have been able to write the solution to this problem in the most optimal way. So time complexity I've already discussed. It is O of n, because firstly we are doing it in the single traversal, and all the operations that we are doing in the DQ, whether we are adding, removing, doing a peek, everything is done in constant time. And we have not taken any additional space, so that's going to be constant as well. So yeah, that is all about this particular question. Sliding window maximum. The code is going to be available in the GitHub. The link to that is in the description, so do check it out. Please do a dry run before and then start practicing the code for this. And thank you so much for watching today's video. Hope you guys have got some value out of it. And if you have, please don't forget to like and share. And please don't forget to subscribe to the channel as well if you haven't already. Thank you so much.